Steve is the Wayne and Elizabeth Jones Professor of Mathematics at Northwestern. He received his PhD from Berkeley in 1981 under the direction of Alan Weinstein. And after a postdoc at Columbia, he moved to Johns Hopkins in 1986, and he stayed there until moving to Northwestern in 2010. Steve has received many honors. He spoke at the ICM in Beijing in 2004, and he gave an invited AMS national address in 2005. In 2013, he won the Bergman Prize for his work, which, according to, quote, infused the whole subject, which is to say the Bergman kernel, with a new vitality. So Steve is well known for his work in complex geometry, probability, and mathematical physics, and we're delighted that he's agreed to come and give this fall Simons lectures. So the title, as you can see, is Planck's constant, time, and stationary states in quantum mechanics. And the current plan, so there'll be 3 lectures at 4 o'clock today, tomorrow, and Thursday. The current plan is to hold the next 2 across the hall in 102. So Steve, thank you very much.
All right. First of all, is this on? Seems like it's on. Okay, well, thank you very much for the invitation to speak, and thank you to the audience for coming to my talk. So, what I am planning to do is to survey results on the semi-classical limit. That's, in this case, the limit as the eigenvalue tends to infinity of eigenfunctions of the Laplace operator on a Riemannian manifold of any general dimension. So the results involve zero sets, that's nodal sets, LP norms, matrix elements. Those are the main things one studies with eigenfunctions. And the main goal is to relate them to the dynamics of the geodesic flow on the Riemannian manifold. Now, it's a very classical topic in PDE, but I want to start by just recalling just the very basic facts about quantum mechanics which motivate one to study this problem. So let's go back to roughly 1900 when people were first trying to model an atom. So I'm really covering what is essentially the first paragraph of Landau and Lifshitz' book on quantum mechanics. So quantum mechanics was invented to resolve a puzzle about the stability of atoms. So before quantum mechanics was invented, it was around the time of Rutherford, people agreed that an atom was a real physical thing, and they could see that it had a nucleus and that there was an electron that was kind of orbiting around it in some sense. And so the original model, let's say you might learn in high school, is that a hydrogen atom is like a planetary system with a nucleus at the center and an electron orbiting around it. So that's like just like a two-body problem, Kepler problem. This is a Hamiltonian dynamical system with the form kinetic plus potential energy, and the potential energy is the Coulomb force. Okay, now of course it differs from a planetary system because this is a positive charge and that is a negative charge. However, that couldn't possibly be correct, as people realized instantly, because the moving electron would radiate electromagnetic radiation and lose energy and spiral into the proton instantly. So how are they supposed to figure out how to model an atom? They want to have a classical picture of it, but that's too naive. So Bohr came up with the idea that the picture is more or less correct, but the electron can only occupy certain orbitals. So this is sort of the Bohr-Sommerfeld picture of a hydrogen atom, namely that you have the nucleus still, but the electron cannot exist in all possible orbits, so it can only exist in these very discrete set of orbits. These are the bound states of the hydrogen atom. And there is a quantization condition for which of these orbits the electron can be moving around in. And the quantization condition is that the action integral, the integral of the form PdQ, around the orbit gamma should, roughly speaking, be an integer times Planck's constant. Okay. Now that's a semi-classical theory. There's a kind of classical mechanical description of the quantum mechanical object. The energy levels are determined by special classical orbits satisfying quantization condition. But very rapidly, this theory correctly predicted energy levels of a hydrogen atom, but it can't be used for more complicated atoms. As soon as you get to 2 electrons with a helium atom, you have very few periodic orbits. You can't possibly try to explain which the quantum mechanics in terms of quantizable periodic orbits. As a matter of fact, just trying to understand what the periodic orbits are is a big problem. That theory couldn't possibly go in. Three-body problem. So that theory is either insanely complicated or just plain hopeless. So that can't be the generalization of it. And then around 1926, a completely different theory was introduced by the famous founders of quantum mechanics. So in particular, my talks have to do with Schrodinger's way of doing this. So he wrote a paper called Quantization as an Eigenvalue Problem. And he said, instead of trying to model the quantum mechanical object as a point moving around, think of it as a function in L2 of the space. Okay, that's this thing called phi j, the wave function. And the energy states, the states of the electron in which have a determined energy, are eigenfunctions of this Schrodinger operator. So this is the kinetic energy term. You quantize, so to speak, c squared by minus h bar squared times the Laplacian, h bar being Planck's constant. The potential gets quantized as multiplication by the potential. And you have a eigenvalue problem which resembles very classical things that people study for vibrating drums. So, there was a kind of a stunning leap of imagination, and yet it led to very classical kinds of PDE problems. So why does this resolve the problem? In a sense, what we're doing is we're replacing classical mechanics with linear algebra. Namely, when we try to understand the time evolution of an energy state of a particle with a fixed energy, then we have an evolution operator, the propagator, u sub h of t, is just e to the minus it over Planck's constant times the Schrodinger operator. And if you put phi j, if phi j is an eigenfunction of the Schrodinger operator of the operator in the exponent, then it is also an eigenfunction of the propagator, and you just exponentiate the eigenvalue. So why is this going to solve this problem about the stability of atoms? Well, because the only quantities that are observable in quantum mechanics, according to the Born interpretation, are the modulus squared of the eigenfunction. This is the probability density of finding a particle at x. So it's interesting that the eigenfunction itself is not a probability. It's mod squared is a probability. And you can observe, these are called the expected values of observables in these quantum states. So these are called in math a matrix elements of an operator A. So in this basis phi j. So when I write down phi j, I'm thinking of finding an orthonormal basis of eigenfunctions for the Schrodinger operator. So the particle evolves just by if it's in a stationary state, if it's an eigenfunction, it just evolves by multiplying it by this complex number of unit modulus. And then you see that the mod squared does not change. And you see that if you look at this matrix element and you plug in ut of phi, you just plug in complex numbers, and of course it comes out with a complex conjugate and cancels it. So the expected value doesn't change either. So these phi j's evolve to all intents and purposes in terms of all observations as if they were stationary. And in fact, in the textbooks, they are called stationary states. They're not moving. So quantum mechanics resolve this puzzle of how an electron can be moving and stationary at the same time. However, there's a price to pay for this new point of view, which is that you're replacing the Bohr model, which was geometrical, it was classical mechanical, we could picture it, by eigenfunctions of some operator, which, well, a priori, we have no idea how to understand them geometrically. In fact, for the hydrogen atom, they're functions of 3 on R3. If we have a helium atom, they're going to be functions on R6, let's say. I mean, they're eigenfunctions on very high dimensional manifolds. So first question is, why was the Bohr theory correct? I mean, it was a theory that tried to relate the energy levels and the eigenfunctions to orbits. How could it have worked if this is the correct interpretation? The second one is, how are we going to be able to relate eigenfunctions to classical mechanics? If we cannot somehow relate the eigenfunctions to classical mechanics, we can't really understand them at all. So here's a picture. We'll see a lot of pictures in the next few slides. This is a picture of the first 25 energy states of the hydrogen atom. So in the ground state, this is the graph of psi squared. So these are called intensity plots, where you take the norm of psi squared, norm of phi squared, and you draw it in with yellow where it's biggest, and then red where it's pretty big, and then black where it's really small. So we see that it looks kind of really localized right at the nucleus in the ground state. It looks like almost like a point. It's spherically symmetric. And then
what's the domain of phi j? Function of what?
This is phi j squared we're looking at.
It's a function on
R3.
What's the independent variable?
We're looking at it on R2. We're looking at just like a plot of phi j squared. Okay, so we should be looking on R3, but we're kind of projecting it, right? I mean, it's the only way we can draw a picture, right? So, okay, so as you start moving up, you start seeing more complicated shapes that phi squared can have. These are angular momentum states. In these states here, it's radial. There's zero angular momentum. And then you start seeing higher angular momentum, and the picture becomes more complicated as the eigenvalue goes up. And indeed, that's in a sense what the semi-classical or high-energy limit is all about. It's trying to understand the asymptotics of these more and more complicated shapes, either as h goes to 0 or as the energy goes to infinity. All right, so the goal is to understand the sizes and shapes of the eigenfunctions of Schrodinger operators and to try to relate them to classical mechanics in the semi-classical limit. So as I said before, the modulus squared represents the probability density of finding the particle at x. Probably the most interesting thing you could try to understand graphically, or you could try to prove a theorem about, is trying to get some geometrical idea of the set of points where phi j squared is very large. So this is what a probabilist would call an excursion set. You'd like to understand a super level set, the place where phi squared is very large. So here are some more pictures. We'll be talking more about this one here. But these are essentially like spherical harmonics. And this is like an eigenfunction which is very large here, fairly large in the middle. Here's more of these intensity plots. And you can see that there are quite a variety of different kinds of geometric shapes that you can get. So this is still, we're just discussing the hydrogen atom.
We're darkened off into the region where it's large?
Where the white part is where it's large.
White part where it's large?
Yes.
Okay.
Is there another question? Okay. So on the other hand, you might try to understand the points where it is as small as possible, namely the zero set. So the zero set is called the nodal set. It's not so easy to find good things on the web, so this is the best I could do, where the nodal set were these things called nodal planes. If you look in a textbook on physical chemistry, physical chemists must understand the actual graphics. And so either they draw where it's large or they try to draw the nodal set. You see the nodal set quite a lot. Now, let's see if I'm going to say that on the next slide. I guess not. So, phi j squared, where it's large, which I'm sort of calling the excursion set, is probably the most interesting thing you could study, because that's where it's most likely to find the quantum particle. That's what you'd like to know. In a sense, the nodal set is the place where the particle is least likely to be, because phi j squared is the probability. So these are the points where the probability density vanishes, and we're not likely to find it there at all. So, yeah, well, here, by the way, it's kind of interesting that just a couple years ago, experimental physicists were actually able to see the nodal set of some excited states of the hydrogen atom for the first time under some kind of microscope that's been developed. So despite this sounding like ancient history, actually in terms of experimental physics, it's actually contemporary interest to understand these features of hydrogen or other kind of molecules with very few atoms in them. Now, I want to talk more about the nodal sets and critical point sets because, if we want to think mathematically, we might as well go back to just ODEs on an interval. That's the simplest illustration of what we're talking about. And so this is the first place, is a vibrating string. It's the first example, I guess, due to Fourier, of where one actually studies the eigenfunctions of a Schrodinger operator. Just in this case, phi double prime is minus lambda phi. And here I'll put Dirichlet boundary conditions at the edge, and you can explicitly solve for them. And now you see that the ground state has no zeros. It's, of course, zero at the endpoints. It's got Dirichlet boundary conditions. It has no zeros here. And then you have the first excited state, which has 1, 0. You have the second excited state, which has 2. The next one has 3 zeros. Also are interesting, very interesting, in fact, are the local maxima and minima, which are called antinodes in textbooks. So these are, of course, the places where the particle is most likely to be. So in a lot of ways, we would most like to understand the local maxima and minima, especially the ones that are very, very high lying. So in any case, one gets the feeling that as the energy grows up, you can even determine what the energy is by how many critical points the eigenfunction has, how many zeros it has. The regions in between the zeros are called nodal domains. So this has 1 nodal domain, this has 2 nodal domains, 3, 4. You feel like the complexity or the eigenvalue is going to be reflected by the number of critical points, the number of nodal domains, and the number of zeros. That was a very simple one-dimensional example, but the same pattern persists if you look at any one-dimensional example. So these are called Sturm-Liouville equations. So we have a second derivative, and I just put the Planck's constant in. We're really going to be looking at h goes to 0. And okay, so I put a potential in. This is the harmonic oscillator, so we put in an x squared. And again, the ground state looks, it doesn't actually end here. It's e to the minus x squared over 2, so it's really just, dying out very fast. But it has 1 local maxima. Here you have like 1, 1, 0. It has no zeros at all. This one has 1, 0, 2 local maxima. So we see that same pattern being repeated, that as the eigenvalue goes up, you get one more nodal domain, one more critical point. And that's, in a lot of ways, the way that people think about how you detect the energy state is by counting the number of nodal domains, critical points, things like that. Well, a naive idea, which was of some interest in the 70s, let's say, a rather naive idea was that if you go up in dimension, you're going to see a similar kind of situation where the nth eigenfunction has maybe n nodal domains and n squared critical points. But as it turns out, the naive idea that this pattern is going to persist, that we can figure out what the energy level is by counting the number of critical points or nodal domains, it turns out to be completely wrong. The eigenfunctions can be very much more complicated in higher dimensions. So even on a standard sphere or a square, you can find sequences of eigenfunctions where the eigenvalue tends to infinity, which have just 2 or 3 nodal domains, which have just 10 critical points. So we can't exactly measure the complexity of the eigenfunction by the number of nodal domains or the number of critical points. Now, people thought at first you should be able to do that because the simplest possible eigenfunctions and the only ones that to this day can be explicitly computed are separation of variables cases, where you can write the eigenfunction as a function of x times a function of y. So that's what happens if you have a completely integrable system on the quantum mechanical level. And but anyway, what happens? Well, then, if you look at these sort of separation of variables product eigenfunctions, you get kind of checkerboard patterns. And these do behave very similar to the one-dimensional case because they're just products of one-dimensional eigenfunctions. And as you go up in energy, you start developing more and more nodal domains. These points where these are nodal lines. The boundaries of the shaded region is a 0 set. That's a nodal line. Here you have a point where 2 nodal lines cross each other. So this one here is called a singular point. It's a point where the eigenfunction and its gradient both vanish. So it looks as if you're getting more singular points, therefore more critical points. Clearly, inside each nodal domain, you have to have a local maximum or minimum because the function is, let's say, positive in the black square and negative in the white square. So it's going to have it's 0 on the boundary, 0 on the boundary of a nodal domain. So it's going to have a local minimum in the negative one or a local maximum in the positive one. So if you have a lot of nodal domains, you're also going to have a lot of local maxima and minima. However, if you are on even a square, you have multiplicity to the eigenvalues. And these are just very special separation of variables eigenfunctions. If you make a small perturbation of the eigenfunction, first of all, generically, there won't be any singular points at all. So there won't be any crossings of the nodal lines. They will be just smooth circles. So this is really more typical of what a nodal set is going to look like. You're going to have some complicated topological pattern of nested nodal sets, and it's not clear how many nodal sets there are. So that brings us to the kinds of questions that, PDE type questions that people want to study. So how do you relate the asymptotics of nodal sets, LP norms, that measures how large the eigenfunction is, and critical points or other features of the eigenfunction as the energy or the eigenvalue increases to infinity? So going back to the Bohr model, the whole point is that as the eigenvalue goes to infinity or as h goes to 0, the quantum mechanics is supposed to go back to the classical mechanics. So somehow you should have some geometric asymptotics for these features of eigenfunctions, relating them to dynamics of the geodesic flow. So the purpose of these lectures is to survey some recent results on nodal sets and nodal domains. So first of all, one of the problems is to count the number of nodal domains. In general, there are almost no results. In fact, the only results on counting nodal domains appeared within the last year. And the only case where it's possible, except in really trivial cases where you can separate variables, is when the geodesic flow is ergodic. So somehow we can't understand how every kind of dynamics of the geodesic flow impacts on eigenfunctions, but ergodicity actually constrains a lot the behavior of the eigenfunctions. Okay. Secondly, there are some recent results of the volume of nodal sets. And as I'll explain in a few minutes, in some cases, well, in the ergodic case, we can actually even discuss how the nodal set is equidistributed on the manifold. But as I'll explain, we can only do this in the complex domain. We don't know how to do it in the real domain. All right? And secondly, I want to discuss some new results on the LP norms of eigenfunctions. So, in particular, let's say when p is equal to infinity, there are certain universal bounds on how large L2 normalized eigenfunction can be. And these bounds are achieved by very special functions, in fact, the ones that we saw in the hydrogen atom. But for a typical Riemannian manifold, the eigenfunctions will be smaller than they are in the case of the hydrogen atom. So I want to discuss what is the geometry, what is the geodesic geometry of a Riemannian manifold where one has extremely large eigenfunctions. So now let me introduce the mathematical objects. There's one natural second-order operator on a Riemannian manifold called the Laplace operator. So this is associated to the Dirichlet form, which is the integral of grad phi squared. And we're never going to be using it, but this is a formula and turn local coordinates for the Laplace operator. And it's not hard to prove, it's a classical theorem going back to the days of Hilbert and Curran, that on a compact Riemannian manifold, this operator has an orthonormal as a discrete spectrum of eigenvalues, no points of accumulation except at infinity, and there's an orthonormal basis of eigenfunctions. So the eigenvalues are negative, so I write them as minus lambda j squared. This is a somewhat unusual choice of notation. People usually just use lambda j here, so this could get pretty confusing if you're used to the other notation. And they're assumed to be orthogonal to each other. And I'll use the notation ncal for the nodal set. Now I want to start off by giving mathematical intuitions about eigenfunctions. So, compared to, we're only going to be studying this equation. So, this looks like a very simple PDE. You might think that everything is known about it. But what happens when you study a simple equation is that you ask very difficult questions about the solutions. So, of course, there's no question about when they exist and so forth. This is settled 100 years ago. It's really more about how they're related to the classical mechanics. That's the kind of question which is still not known. Okay, so what do we like to know? Well, the square root of the eigenvalue is usually called the frequency. 1 over it is the wavelength. So these eigenfunctions are very rapidly oscillating. They go up and down on the length scale of 1 over the square root of the eigenvalue. So if you're used to studying elliptic equations, like the harmonic equation where you would have this equal to 0, harmonic functions, like in dimension 1, these are just like line segments. They don't oscillate. So the fact that we have a lambda j squared here completely changes usual elliptic theory. Now, this lambda j, the main intuition people follow for the last 30 years is that the square root of the eigenvalue should be thought of as like the degree of a polynomial. So if you look at a spherical harmonic, an eigenfunction of the Laplace operator on the standard sphere, an eigenfunction of eigenvalue n squared is just the restriction to the sphere of a harmonic homogeneous polynomial of degree n. So in the case of a standard sphere, we are just studying the zero set is just a branch of real algebraic geometry. Now, if you are on a general Riemannian manifold, studying the nodal set of an eigenfunction is the analog of doing real algebraic geometry on the Riemannian manifold. But there are two ways in which that statement's not exactly correct. First of all, a real polynomial doesn't need to have any real zeros. However, eigenfunctions have a lot of zeros. So one of the first theorems in the subject, which was proved by Courant in the 20s, was that in every ball of radius, so there's a number a depending only on the metric, so that in every ball of radius a over the square root of the eigenvalue, there is a zero of the eigenfunction. In other words, the nodal set is 1 over lambda dense in the manifold. So that's something where you have to use the equation here to prove it. It's not even obvious for these harmonic homogeneous polynomials. All right, so eigenfunctions are like polynomials, but not just any polynomial. And it's not really that obvious why the zero set of an eigenfunction is not at all like the zero set of a typical real polynomial on Rn. They're rather special. Of course, we have to use this equation rather than using algebraic geometry to understand them. Now, the second thing is, if I polled the audience before this talk and I asked, what kind of an equation is this? Everybody would probably say it's an elliptic equation. The Laplace operator is the archetype of an elliptic operator. But that's both true and false. And the fact that it's both true and false permeates the methods of the field. So, in other words, the question is, should I keep this term in as part of the principal symbol of the operator? So when you take the principal symbol of the Laplacian, you just get minus c squared. All right, change the sign here. So c squared. The symbol of the Laplacian is just the length squared of a covector on the cotangent bundle. If I don't put in the lambda squared, then this one will be 0 only when momentum c is equal to 0. But if I keep in this, which is the semi-classical definition, then this thing vanishes on the energy surface of covectors whose norm is equal to lambda. And of course, so this is going to be mainly the correct definition. So what moral do we draw? An equation is called elliptic if the principal symbol never vanishes, unless c is 0. So from this semi-classical definition, this is not an elliptic operator. All right, so what is the actual facts? And so the field actually splits into two groups of kinds of people. So on the one hand, it turns out that if you study this equation here on really, really small balls whose radius is of the size of some epsilon divided by the square root of the eigenvalue. Those are called very small balls. Then it turns out on those small balls, the equation is elliptic. You can actually rescale the whole equation and put it on a ball of unit size. And it turns out that you will get a rescaled version of this equation where all the usual elliptic theory works. So if you've ever studied this, the elliptic people are, for example, like Charles Pfefferman or Fanghua Lin. So there are many people, Bears. There are many people who just only put the equation on a small ball, rescale it, and then try to add up everything that happens on all those small balls. That is what a harmonic analyst does. On the other hand, how are you ever going to make contact between quantum mechanics and classical mechanics if you're working on that length scale? What that effectively did was convert this into a Euclidean equation on a small ball. You just completely destroyed the geodesic geometry, the Riemannian geometry, when you put it on that length scale. So the other group, which are called the microlocal analysts or the semi-classical analysts, are people who say it's really a hyperbolic equation. This is really the wave equation, where this thing over here could be think of as d squared by dt squared. It's really the wave equation, essentially. And we have to use wave equation methods. And these are global. We want to understand how the global geometry of the manifold and the geodesic flow is reflected by the behavior of the eigenfunctions. So this is elliptic versus hyperbolic, but you can also think of this as local versus global analysis of eigenfunctions. Incidentally, both methods are very powerful. And there are results where the small ball results are better than what have been achieved by the hyperbolic methods, but then there are things here that you simply cannot see on the scale. I should add the names of Kolding, Menikotsi, Cheeger, Neighbor, who have been studying this kind of problem more recently. Again, and they all do it by using these elliptic techniques. So now let me go through some theorems that people have been able to prove. So this is, the reason why you study nodal, namely zero sets, and you study LP norms simultaneously is that you're sort of guided by complex analysis, where starting with Jensen's formula, you try to relate the growth of an eigenfunction to growth of its zeros. Now this is not standard Jensen formula because we're on a compact manifold, we're not expanding balls. Rather, we have a one parameter family of functions, the eigenfunction depending on the eigenvalue, and we're trying to understand how the growth rate as the eigenvalue tends to infinity of the size of the eigenfunction is related to the growth rate of its zero set. You can also play that game in complex analysis, and that's something people have been doing for the last 20 years, with many of the same techniques. So what are nodal domains? So we take the manifold and we delete the zero set from the manifold, and that breaks up the manifold into a certain number of nodal domains. So for a generic metric, 0 is a regular value for every eigenfunction, and the level set, the nodal set, is just a union of smooth hypersurfaces. In 2 dimensions, it's just a union of curves. When 0 is not a regular value, the curves self-intersect, and there's a local structure to these things. We'll probably suppress these singular points where the function and its gradient vanish throughout. They are of codimension 1 in the nodal set, codimension 2 in the original manifold, so it's actually fairly harmless if you're studying Hausdorff dimension to just delete them. So a classic theorem back in the 20s is that the nth eigenfunction has no more than n nodal domains. So this is very much just the situation in dimension 1, and just saying that the situation in dimension 1 is like an upper bound in all dimensions. In dimension 1, we had like n minus 1 zeros of the nth eigenfunction, and it has n nodal domains. I should mention that this is far from being sharp. I don't want to get into it too much, but there's a classic improvement of this that puts a certain constant of roughly 2/3 here. There's a very recent result last year of Bourgain, which improved it again. And I should, by the way, probably mention that this is a kind of hot topic right now in probability theory, to understand in some probabilistic or statistical sense how many nodal domains these eigenfunctions have. All right, but it's not known if there are any lower bounds. What are the lower bounds? Do you actually even have to have that the number of nodal domains grows with the eigenvalue? So just to go back to a picture again, these are the simplest separation of variable examples. This has 2 nodal domains. This one has 1, 2, 3, 4, 5, 6. Remember that, the boundary between the nodal domains is the zero set, and the function changes sign as you go from across the nodal set. Now here's what a much more realistic picture of what nodal domains and nodal sets look like. This is a random degree 40 spherical harmonic. Now, if you wanted to count the number of nodal domains, actually you should get some number, I believe it's roughly around 1/10 or something, times n squared nodal domains. This is the recent work of Nazarov and Sodin and other people who have figured out the average number of nodal domains of randomly chosen spherical harmonics. But anyway, there are a lot of them. What is known about volume, the hypersurface measure of the nodal set? So once again, I'm using this way of writing down. So Yau, back in 1978, conjectured that the hypersurface measure of the nodal set, this is the surface measure of the nodal set, should be bounded above and below by constants times the square root of the eigenvalue, which, as I said, is like the degree. Now, you might wonder, like, how did somebody think of this conjecture? Well, if you just use the analogy to real algebraic geometry, they're asking what should be the surface measure of a real algebraic hypersurface of degree lambda. And, well, the upper bound is like Wertinger's formula, that the volume should be like the degree. The lower bound, well, that's mysterious because in general, real algebraic geometry, the polynomial doesn't have any real zeros. So the very fact that you have, well, this is a conjecture, by the way, but the fact that the lower bound is that large, as big as the upper bound instead of the constant, is a statement that eigenfunctions have a rich set of zeros. And that's kind of a mysterious thing. What in the equation is forcing so many zeros? Regarding this conjecture, I'll mention a few things. Bruning actually, almost simultaneously with Yau's conjecture, Bruning and Yau proved that this lower bound was correct in dimension 2. However, as we speak right now, if you just look at general C infinity metrics, this is the best upper bound proof to date. So this subject is far from being understood. Lambda to the lambda is considered just, an insanely bad estimate by everybody. Even getting it to e to the lambda would be probably not, hard, a good paper, but still you're nowhere near what people are doing. Now, probably I would say the best paper written about nodal sets in history is this paper of Donnelly and Pfefferman in 1988. And they said, what if we add the assumption that it's real analytic? Now, for reasons that I will explain as the lectures go on, this puts you in the realm of complex analysis, which is far more powerful in this field than real variable techniques. And so, in fact, I can give a 2-page proof of this upper bound now using global complex analysis methods, very similar to the kinds of things people use in plurisubharmonic function theory now. They proved that the Yau conjecture is correct for the real analytic case.
So doesn't that prove it? Is the infinity case morally?
No, afraid not. So that just shows you how much we know about smooth functions. There's no way you can just, you would have to approximate it's not, people actually try to prove these things. That's how, remember, this is Hart and Simon who are experts on how you make these kinds of approximations. Their whole technique is to approximate the eigenfunctions in the C infinity case by harmonic polynomials locally. In fact, this is what Cheeger-Neighbor do. This is what Fang-Hua Lin does. This is the local technique. It is an approximation. And you have a lot of small balls to work with when you start doing it. So you can get a pretty good approximation on a small ball, and you can get a pretty nice estimate on a small ball, but you're going to have lambda to the n small balls, so you're not going to get, in the end, anything very good. If you were, people would have been able to improve this terrible result. But, try it and see. See if you can improve on that. So, in dimension 2, by the way, there's a better upper bound. That's the only dimension where there's a better upper bound, and a rather beautiful paper by Rui Taodong in the 80s, which got this. Donnelly and Pfefferman by something else got that. What else do we know? First of all, as I mentioned, we know that the whole idea that the number of nodal domains and critical points is going to go up with the eigenvalue is completely incorrect. So Hans Levy in 1980s proved that you can find sequences of spherical harmonics of arbitrarily large degree which have only 3 nodal domains. So, all right, that nodal line just snakes all over the place. It was proved by Nadia Jacobson and Nadia Rashvili a few years ago that for some other metrics on the 2 torus, the number of critical points is bounded above by 10. So that would be very difficult to understand for these eigenfunctions, where the particle is likely to be. So a conjecture, I guess I made this conjecture, but I mean anybody would believe it in the subject. I mean, these are just special sequences of eigenfunctions where you have so few nodal domains, where you have so few critical points. Surely this is really anomalous behavior. And at least there should exist some sequence of eigenfunctions where the number of nodal domains tends to infinity. These bizarre things with only 3 nodal domains, that shouldn't happen very often.
Do they also have high multiplicity? Or?
Well, what are? You mean, what do you mean? You mean in the case of a sphere they are?
The torus.
No, this was not a standard metric. They constructed the metric to produce eigenfunctions with this property, so it's not any kind of standard metric. Yeah, I don't think the multiplicities are probably 1. All right, now I don't want to harp on this too much, but fairly recently, Sog and myself and Kolding-Minikotzi at least got out of this dismal territory. The best result was Fanghua Lin, which said that the lower bound on the Hausdorff measure in higher dimensions was e to the minus lambda. That was kind of horrible. And simultaneously, using completely different methods, we both proved this lower bound. So notice that in dimension 3, it says that the measure is constant. When the dimension's 4 and higher, this number is tending to 0. So it's saying that the nodal set might not have very much volume, but at least it's not exponentially small. So Kolding-Minikotzi, by the way, did it by using the Donnelly-Pfefferman small ball methods. We use something global. And this method here has been tweaked by quite a number of authors since then. And Hamid Hazari and Sog got a very, very good modification of our proof and showed that, in fact, the Hausdorff measure is greater than what Yau claimed it was, but multiplied by the L1 norm of the eigenfunction. So this is an example of how big LP norm implies lot of nodal set. And with Sog and my proof also related the nodal set to the L1 norm. And, when we did that, we thought, we're going to prove Yau's conjecture tomorrow because, gee, the L1 norm, that's a pretty easy thing. I mean, these eigenfunctions are L2 normalized to equal 1. However, there are very, very few results about the L1 norm of eigenfunctions. They can go to 0. They can go to 0 so badly that you get back this answer again. And we don't know when they do and when they don't. Now, I want to get into what strikes me as science. It sounds like science fiction, but I'll explain it isn't. What about distribution of the nodal hypersurfaces? How are they distributed on the surface? Meaning that if you take a function, a continuous function, and you integrate it over the nodal set with respect to surface measure, so think of it as a current of integration. We just integrate it. How does this integral behave as the eigenvalue tends to infinity? Well, if you put in 1, you get the Hausdorff, the surface measure, so it should go like lambda times something, according to Yau. How? What's the coefficient? In other words, how much nodal set do you have in some open set on the manifold? Is the nodal set uniformly distributed or not? And how does this question reflect the geodesic flow? So this is a physics conjecture, at least I invented it and distributed it to the physicists, that if you have at least, let's say, real analytic, and at least where the geodesic flow is ergodic, then for almost all the eigenfunctions, the density 1 sequence, the nodal set should become uniformly distributed on the manifold. If we divide by the square root of the eigenvalue, integrate a function over it, then in the limit it should tend to the average value of the function on the manifold. All right, so there's a certain reason for this, which I don't want to explain. And here's a picture of the ergodic case. And this is a stadium, a Sinai billiard or a Lorentz Sinai billiard, hyperbolic billiard table, where you have these kind of concave walls, and the billiard trajectory is going to have an extremely chaotic behavior in this kind of stadium. And you can see that at least here, you get a uniform gray, so it looks sort of reasonable. Now, there's a now ancient theorem that explains why ergodicity should be a good input into this. Namely, remember that a classically ergodic system is one where the geodesics are kind of uniformly dense. They're traveling around all over the manifold in all possible directions. So they are uniformly dense in the unit cosphere bundle. And roughly 40 years ago, earlier in 72, Schnirelmann announced this, and then myself and then Colin de Verdière and myself and Zaworski in different contexts gave complete proofs of this fact. And it says that if you have ergodic geodesic flow, then the eigenfunctions become equidistributed on the manifold. If you integrate phi j squared over set E, then it tends to the volume of E over the volume of M. And this is actually true in cotangent bundle, not just in M, but it would require too many definitions to state it in the cotangent bundle. But roughly speaking, this is the probability of the particle being in the set E. And if quantum mechanics tends to classical mechanics, this should tend to the probability of the classical particle being in E. And by ergodicity, that's the relative volume of E. So that's actually a theorem. And ergodicity is really a mechanism for forcing eigenfunctions to oscillate at maximal rates in all possible directions. So ergodicity is should have a lot of zeros. So here are the new results that I want to discuss. First of all, a very recent result with Jung, which is that if we're on a surface of negative curvature, and with a concave boundary, that's like taking a disk outside of actually it could be non-positive curvature. This works on a flat torus if you remove a disk. So if you look at the Sinai billiard, you take a surface of non-positive curvature and with a concave boundary, so this has not just ergodic but highly mixing geodesic flow, then we can prove that the number of nodal domains will tend to infinity along almost the entire sequence of eigenvalues. So, all right. So that's essentially the first example where you can prove that the number of nodal domains is not bounded as the eigenvalue tends to infinity. This is proved by proving that nodal lines in geodesics have to intersect a lot. So this is actually the key technical thing that not just myself, but Borgana and Rudnick and many other people are studying is intersections of nodal lines in geodesics, namely how the eigenfunction vanishes on a geodesic. It's easier to do things in dimension 1 than 0, so when we restrict to geodesics, it's somehow a little bit easier. And we have both upper and lower bounds on the number of zeros that an eigenfunction has on a geodesic. This is something where one really hopes that the results get improved over the next few years. And counting intersections is based on trying to get very good sup norm bounds, L-infinity estimates on eigenfunctions, first of all. And like when are the eigenfunctions really, really large? What kind of geometry can support an eigenfunction that's really, really large? And on something else, which is a kind of restricted version, it's a restricted version of this quantum ergodicity theorem. We want to prove it when we restrict the eigenfunction to a curve. So this involves a new result with Sog and myself. In fact, as I stated now, it's only 2 weeks old, which is that if you have at least a real analytic surface, and if the eigenfunctions achieve a maximal soup norm bounds, then there has to be a point P like the North Pole on the sphere, so that every single geodesic leaving the point P is closed. Every geodesic is closed at some point. So that's a very rare property of a metric, but there are plenty of them which have that property. So there has to be some kind of a pole. And then, I personally, because I like complex analysis, I want to study the analytic continuation of eigenfunctions to the complexification of the manifold. So the complexification of the manifold is just the cotangent bundle. We're just putting a complex structure on the cotangent bundle. And I want to see the zero set in the complex domain. So these are now like complex analytic hypersurfaces. And we know in algebraic geometry that the complex hypersurface is much simpler to study than the real one. And it turns out to really be very true here. We can actually determine how the nodal set in the complex domain becomes equidistributed in the cotangent bundle as the eigenvalue tends to infinity. So I think we started a bit late. I just want to spend maybe 5 more minutes sort of stating the results a little bit more concretely. So first of all, if you're not in the subject, it may not seem to you like, the number one goal of your work, but nevertheless, it's been a problem for many years to try to show that the number of nodal domains goes to infinity. So I want to prove this in 2 different cases. The proofs are actually quite similar. First of all, I want to show that the number of nodal domains goes to infinity when you have a non-positively curved surface with concave boundary. That's what's called the Sinai billiard. And the second one is a boundaryless analog of this. And this has to do with a Riemann surface, what's called the real Riemann surface. So it has an anti-holomorphic involution. And so it's the complexification of a real algebraic curve. And I can only prove it in the case where the fixed point set, the underlying real locus, separates the Riemann surface into 2 connected components. So that's a topological or a complex analytic restriction on what the surface is, but we can put any negatively curved metric on it. So we still have these very large families of metrics for which we can prove it's true. So here's the statement that if we want to count the number of nodal domains and we take a surface with non-positive curvature and we remove a disk from it, then for any orthonormal basis, you can find what's called a density 1 subsequence of the indices here, so that the number of nodal domains tends to infinity. Okay? And here's what a Sinai billiard looks like. If you even took like a standard square, which has completely integral billiards, and you remove a hole in it, then this will become hyperbolic. This is a Sinai billiard. The thing just has to bounce. It'll bounce very erratically off. It bounces nicely off the inner one, bounces nicely off the outer one, but they're not synchronized, so that it ends up being very chaotic. And maybe I'll skip that one. And so by density 1, that's an important definition. I mean that the eigenfunctions which have the good property, if we count the number less than n, then divide by n, the number goes to 1. So we're only removing a sparse set of possible eigenvalues where the behavior is not like that. And here's an example of I should not have said hyperelliptic. Here's an example of a Riemann surface with anti-holomorphic involution exchanging the top and the bottom. So this surface is one for which if you put any negatively curved metric on it, the eigenfunctions will have this property. Now, I should mention that this theorem was inspired by an earlier theorem of Gauss, Reznikov, and Sarnak. So they proved a kind of a similar result in this setting, the modular curve. So for them, the geodesic, they use this central geodesic. It's, of course, non-compact. And they proved their theorem for what are called Maas-Hecke eigenfunctions, which are eigenfunctions of Hecke operators. And they also proved that you have the number of nodal domains. They gave a very nice power law, lower bound, for how that did. So that is much stronger than what we're proving. We're just proving the number goes to infinity. And if we work very hard, we can get it to go to infinity at a log rate. On the other hand, there are very special eigenfunctions because these are eigenfunctions of Hecke operators, and they assume the Lindelof hypothesis for what are called Maas-Hecke functions. So it's not an actual theorem about eigenfunctions. It's just a conditional statement. Everybody believes the Lindelof hypothesis. All right. Now, I just want to say one thing about the equidistribution of nodal sets. So remember, we have this conjecture that the nodal set becomes uniformly distributed on the surface if the geodesic flow is ergodic. And this is completely science fiction to try to prove this result. However, it turns out that when we go into the complex domain, we can actually prove it. So these are the theorems I want to discuss in the complex domain. So the complex geometry is interesting just, I think, intrinsically. When you complexify a real analytic manifold, you get what's called a Grauer tube, which is a strictly pseudo-convex domain inside the cotangent bundle. And so it's plurisubharmonic analysis, which produces this kind of result. And so if you have a real analytic and the geodesic flow is ergodic, then I have to look at what's called the Grauer tube. So this is really taking place in the complexification of the manifold. This is the complexification of the nodal set. I'm taking the eigenfunction, and analytically extending it to the complexification of the manifold. So then we get a limit formula for how the nodal set becomes distributed in the complex domain. So this is actually a kind of ancient result, but in recent work, we've been extending this in quite a number of different directions. So one is to restrict everything to a geodesic rather than working globally on the manifold. These intersection points, as I hinted, are useful for many kinds of other problems. So we want to understand how it works, and I got an equidistribution result when you restrict it. But I want to also go over this kind of result. So, okay, so I'll stop here.
The statement of the last about the zeros coalescing on the. Yes.
So this statement over here is what happens when you look at intersection points. So this thing about nodal domains that I'm mentioning is all based on showing eigenfunctions have lots of zeros on a geodesic. An intersection point. So I wish there was some chalk around here, but here it is. So I mean, here's a surface. Here's M. And then the nodal set, often consists of a lot of these things, but could have who knows exactly how this thing behaves. That's the nodal set. Now let's pick a geodesic, gamma, and look at the intersection. So we're just restricting the eigenfunction to a geodesic, and it turns out it's a very useful thing to do. Now, in the real domain, we could only prove that the number of intersection points tends to infinity. But if you complexify the geodesic and look at the number of complex zeros on the complex geodesic, then they grow at the rate square root of the eigenvalue. And in fact, they not just do that, but they kind of condense on the real geodesic. They're not like uniformly distributed in a strip, in the complex strip. They're really clustered around the real geodesic. So indeed, I believe that the number of real zeros is of the order of lambda. And the real zeros probably become equidistributed along the real geodesic. But our control in the complex domain is so much better than in the real domain that while we can prove this in the complex domain, we can't even make that imply a better result in the real domain. So, okay.
You mentioned this result, which went by very quickly, but very, very interesting looking result about the existence of points where all of the geodesics are closed through the particular point.
Yeah, I'll talk about that tomorrow.
All right, so.
Well, what was the question now?
I was going to say, could you put that in the more specific context of characterizing the Nodal metrics?
See, it's much less than a Zoll metric, because a Zoll metric has the property that through every point, all the geodesics are closed. And I'm just saying there's one point on the manifold for which all the geodesics are closed. So if the soup norm blows up, then it's going to blow up. Well, in general, the point where the eigenfunction is huge can move all over the manifold. But if you imagine that at this one point where the eigenfunctions are blowing up, there's some focusing property of geodesics going on, which is responsible for the eigenfunction blowing up. So that's why they all turn out to be closed. The fact that they're smoothly closed actually uses a little result in dynamical systems. So it's not just pure PDE method.